Hi, welcome back to our next section. Last time we are mentioned about the verified or measure of center, which is covered a couple of different topics about the mean, median, the mode, and even the mid-range, as whatever we have seen for the measure of center. Then another good measure, numerically, is the measure of variation. One measure of variation, it measures the consistency among the data values. And the first thing we can find is the range. Range itself simply is just the maximum minus the minimum. The maximum value minus the minimum value, which is pretty clear what it is, but they just say, well, how wide a group of data is, right, from minimum to maximum, but we don't know where they are, but at least that tells how wide it is. Well, given 4 cookies, count the number of chocolate chips on them, and we get that, well, 4 numbers that are 22, 22, 26, and 24, which from them we can see the largest is 26, the smallest are 22s. Well, which we can find is the range is the maximum 26 minus the minimum 22 equals 4. Right, the range is 4. Well, it's just one type of data can show that how wide the data is. How wide the data set is. But another measure of variation, which more commonly used than the range, another thing more commonly used is the standard deviation. Sample standard deviation, which the sample standard deviation, the notation is the lowercase s, is a measure of how much data value deviate away from the mean. How much is the data value deviate away from the mean? That is called the standard deviation. If it's from a sample, then the notation is S for the sample standard deviation. By definition, is for each individual data minus the mean from the sample, then we add them together. Right, that is what it is, but it only happens is, well, that follows the same level as the data is, which is the first order of the level. Right, but the problem is we add everything. The mean is, if you remember, right, if the sample mean is sample of x divided by n. Right, for some reason, if we adding this thing, what we'll get is the value if we get from left or from right of the sample mean, we add all together, we get at the end will be 0. Right, if we simply do that for some calculation we do later, we'll get a 0 at the end, which is not showing anything. Right, that doesn't show anything. So, because some data is negative, some difference is negative, some difference is positive, right, then what we do is squaring it and take the average. Right. We have n minus 1 as the denominator is because, well, if the sample mean is set, we'll have not the n data are free, but only n minus 1 data are free. The last one, if we know the sample mean itself, right, the last data is not free. Like we have sample mean is defined, and if we have 4 numbers, once the first 3 data is defined, right, it fits. It's free variable, right? If it's free, but if there are fits, then the last one has to be fits due to the sample mean is already known. Therefore, it will lose 1 degree of freedom to make it its unbiased estimator in a way. But that is the formula. We get sample mean S equals that. But it is under square root since we square this difference. Right? Since we square the difference, what we do is sum everything, divide by minus 1 for sure, we get positive or at least in the negative numbers. That is to see how much data away from the sample mean. We square the difference and take the sum divided by the number of data we have. We use n minus 1 to divide instead. And since that's second order, so we take the square root to make it the standard deviation. Right, that is the definition formula and compute. We can use the computational formula, that's sum of x squared minus the square of sum of x, then divided by n minus 1. Well, the computation formula looks a little longer, right? Which we need is square the sum, and we need square the individual and take the sum. That we need to do division and need to subtract. Looks a little more tricky, right? But if for the individual number is not that hard to do, that one is good enough to work with. right? And also if we see, well, we need to take the sample mean in the definition formula, then we need to take the square, we need to take the difference. In that case, right, if our sample mean is not a whole number, even one digit of decimal, when we square it will become a nightmare, right, after we sum everything together. That's a lot of digits of decimals, simply. And when we're doing the calculation here, at least what we do is just sum and squaring, right? So nothing else we touch with the sample mean, but only the individual data itself. So at least maybe a little more beneficial doing with the computation formula, right? Coming out with some reason. Right, then also the thing called variance. Right, they are related. The standard deviation and the variance are related. That variance is just the square of standard deviation, which for the sample that is just the part underneath our square root. That thing is called variance. I consider that the computational formula is developed from the definition that the sum of x minus x bar squared is, when we expand, will turn into this form. Sum of x squared minus the square of sum of x over n, that these two numerators shall be equivalent. Right, so that is the sample variance. Let's see. Some examples. Right, but before we move on, right, what we can observe is this thing is never negative. We get the numerator of our sample variance, right? The numerator of it has to be at least 0 or positive number. It will never be negative. The sample standard deviation has same unit as the original data. Right, it has same unit. Right, so steps using the definition formula. Right, for use the definition formula, that if you still remember, right, that is the square root underneath the sum of x minus x bar squared over n minus 1. Right, first we do is we need to looking for the sample mean. After we compute the sample mean, subtract mean from each invigilator. The result is x minus x bar. Right, subtract the mean from each data. Then to square the difference, right, this when we square the difference, we'll get is for each one we were squaring it, then add the squares together, that we get is the sum of x minus x bar squared. Right, then divided the result by n minus 1. To get the variance, right, the variance is just the thing after division, right? At the end, take the square root. Well, we get the sample standard deviation is the square root of sample variance. Right, those steps are what we do to find out the variance and the standard deviation. Use our first formula. Right, and what we need to make sure at the end or after we compute it, right, is the numerator have to be not negative, right, should never be negative. Right, so let's see, right, use the first formula to calculate the standard deviation. The variance and the standard deviation. By short notation, you could use VAR for variance, and the standard deviation just use initially SD. Right, that's also appropriate. Right, if variance and the standard deviation. Right, that's what it is. For the sample data 1, 3, 6, 8, 8, 9, and 14. Right, so what we can do with this one is just build the table. Right, build a column of 1, 3, 6, 8, 8, 9, and 14. Then we have another column, need x minus x bar. Then the third column is the square of it. Right, if you want to, just separate them. In the middle. Right, that we get are these, right? So we have to use formula to find the sample mean first, that's sum of x over n. N in our case 1, 2, 3, 4, 5, 6, 7 numbers. Or sum of x we're able to calculate out that 1 plus 3 plus 6 plus 16, right, that's 26 already. 26 plus 23 is 49. So that is 49 over 7, which is 7. For the second column here, that we take the difference. 1 minus the 7 is negative 6. 3 minus 7 is negative 4, and so on. 6 minus 7, negative 1. 8 minus 7 is 1. 1. 9 minus 7 is 2. 14 minus 7 is 7. Well, you can double check to add them up together, right? 1 cancels 1, 2, 7, that's 10. 4 and 6 is also 10, which cancel out to get the 0 as the sum. Right? In process, we can double check our work to see if it's done nicely. Right? This number here in the middle need to be a 0. Right? You could do the summation of the middle column if you want to check the result. Right? Then the third column is the square, right, of what we have. That is the square of the difference we get. The square of negative 4, which is 16. The square of negative 1 is 1. Square of 1 is 1. Square of 2 is 4. 7 is 49. Right, then this column underneath, which is called the sum of x minus x bar squared. Right, since we have the column of x minus x bar squared, we take the sum of it, and we can get what? That's 56. 56 plus 52, that's 108. Right, and then the variance, to find the variance, is variance will be sum of x minus x bar squared over n minus 1. That we get the sum is 108, divided by our sample is count of 7 data minus 1 6. Which is 18. At the end, the standard deviation S that is equal square root of the variance, which is square root of 18. That we use calculator to do that. Right? You could keep 1 digit or 2 digits of decimal or more if you want to, no problem. 2 digits is good enough in usual case of that is a whole number in the data. Right, so to use the first formula, right, we need this first step to find the mean, then to find the difference in the middle column. At the end, we square the middle column and take the sum together, divide it by minus 1 to get the variance. And for the standard deviation, we take square root of the variance. Right, that's the majority, right, variance and the standard deviation. So try this one out. Right? We get data 25, 35, 20, 20 and 40. So find the variance and the standard deviation. We do the similar thing. I just set up a table to get all the data in. Right? 35, 20, 20, and 40. Right, that in the middle we need to take the difference between its and its mean, and then we need to take the square of the middle difference. Right, first of all, the column we get from here is from the data we add together, we get 60, 100, 140. Right, that's the sample mean is the sum divided by n, which n in this case is 5. 140 divided by 5, that is what, 28. Right, the first row we need to find the mean is 28. Right, luckily we get the mean is also the whole number, right, that we can just minus it. 25 minus 28 is negative 3. Right, 35 minus 28 is 7. That's negative 8 when we subtract. 40 minus 28 is 12. Right, so we see we get 19 here. For the negative number, we get a negative 19. So we check the middle is 0. Right, for sure. If the middle is not 0, then something is wrong. We need to double check our work. Right? If the sum is getting wrong, if we get dividing wrong, or somewhere if we subtract it's wrong. We could double check our work. Right, then squaring that. Right, 3 squares 9, 49, 64, 144. And when we add all the numbers together, right, that's 128 and so on, plus 144, that's 272. Right, and we have 58. 272 and 58, we get 330. And nothing else, but just add the column together. Right, so for the variance, we get sample variance, that's the sum of x minus x bar squared. Right, sum of x minus x bar squared over n minus 1. That the sum is 330 in the column we found already, divided by n is 5 minus 1. That is 330 divided by 4. Is 82.5. It's 82.5. Then the standard deviation, we're able to find the s equals square root of s squared. That is square root of 82.5, which use calculator to find it, 9.08. So that is the way we use to find the standard deviation variance. Use the first formula. I basically use the definition. And usually for x is not that large, right? The second formula is more beneficial. Or some other case that, well, if x bar has is not the whole number, it is decimal, maybe 1 digit or 2, then it will be very tricky to take the square for the difference. right? So which means it will be very tricky to use the definition formula. That's why the computational formula is invented, is developed for people to use. So we have a set of data, and observing the formula here, what we need for the variance is just the sum of x squared and the sum of x. Just two things we need. So we get the data of x here, we're just squaring each data, and we need the result from the sum of two columns. We don't even need to find the sample mean, that everything will be calculated inside the formula. So we can build a table of 6, 5, 4, 4, 6, 5, and square it. The formula, the table is much simpler. I will just have two columns. That the first column is the sum of x, which is clearly that the sum, 6 plus 5 plus 4 is 15, and 4 plus 6 plus 5 is also 15, which we get 30 as the sum. And then the second column we just need is to square of our x, which is the square of 6 is 36, the square of 5 is 25, and so on. 16, 16, 36, and 25. Which 36 plus 25, that's 61, plus 16 is 77, doubling that's 154. So computation is a little bit easier. We don't have to do the subtract, we don't have to do the square of the difference, we don't have to do that. What we need is just the individual data and the squaring it, and to find the sum. And then to compute our variance is variance that is sum of x squared minus the square of sum of x over n divided by minus 1, which the sum of x squared is the second column. Sum of x squared, that is our second column. The sum of x is our first column here. So don't be wrong. Also, still the numerator has to be not negative. Sum of x squared, that's 154. Sum of x is 30, but we take the square of 30, divided by a number of data, that's 6 of them. At the end, we divide it by 6 minus 1. Then the numerator, that's 30 squared, which is 900 divided by 6. Is 150, 154 minus 150 is simply just a 4. We subtract 154 minus the square of 30 over 6. That if you use calculator you can find out it is 4. So at least we cannot say it's wrong, because it's not negative, but that's all we can say, right? We are not sure if that's right, but at least it's not wrong. Or could be. Obviously it's not wrong. And we get 0.8 as the variance. Then for standard deviation is the square root of the variance. I just write down the formula that we get square root of 0.8 will be 0.89. Right, that's something also, right, for population. Standard deviation is the computation formula, but we have a notation called sigma. Right, the sigma is the same sigma in Greek letter that we have seen was called also sigma, which is the capital sigma. This one is the lowercase sigma in Greek, right, lowercase sigma. Which the lowercase sigma in statistics usually refer to the standard deviation. That formula is the sum of data minus the mean squared over n, and the square root of it. Right, the square root of difference of data and the mean divided by the size. Which for the population, every data is free, so that is a parameter. So everything underneath is a population variance. Population size. Right, then the population variance is just in notation of sigma squared, which is the thing underneath it. And sample standard deviation also can be built by the formula of sum of x squared minus sum of individual x squared over n divided by n. Right, that was the computation way, but by definition this one was how we find the population standard deviation. Of course underneath a square root. Right, anyhow, and the notation sigma square is just the population variance. Now when we don't discuss about the distribution later in our maybe later chapters 4, 5 or 6, we will see those notations. Right, but anyhow, for this chapter referring to the calculation, we're all gonna use is the sample formula, right? So for x to be the data 10, 5, 0, 15, 20, 20, 15, 25, 0, and 10. Right, for this data, try to find the mean, try to find the variance and standard deviation. Right, so first of all, we need to do is find out the sum. Right, that we add everything together, we'll get the sum to be 120. And we're taking the square of each number, 0, 225, 400, 400, 225, 625, 0, and 100. Right, we'll get the sum of everything, just add together. 225, 400, 400, 25, 625, and 100. You get 2100. Right, so the variance, that is sum of x squared minus sum of x squared over n divided by our n minus 1. Which is sum of x squared is 2100 minus the square of 120 over 10 divided by 10 minus 1. That's 1440. Subtract that's 660 over 9, which is about 73.3333. Or you could keep it as infinite decimal. If more digits are kept, of course more accurate for the standard deviation. For standard deviation, we just take the square root of the variance. In process of variance, recommended to keep 4 digits of decimals, if appropriate. That's square root of 73.3333. We get the standard deviation just after we take the square root, 8.56. Right, so that is how we calculate the variance and standard deviation for the individual data.